What I like about stars is the fact that we can study them in detail, and we can apply physics to the study of stars and the study of exoplanets. In a sense, we can use the stars as laboratories for physics under very extreme conditions that we can't meet in the terrestrial laboratory. And the reason we can do that is that we can make very detailed observations of the internal properties of the stars. And that's really the field of research that I've been working on for my whole career. The fact that we can see waves on the stellar surfaces, just like we see waves in the Earth. And just like for the Earth, we can use those waves to do seismology of the interiors of the stars. So we can measure what conditions are inside the Sun in very great detail, in what we call helioseismology, and we can do similar things in less detail for other stars.
Well, helioseismology, it's the study of the motions of the gas and how the waves that propagate through the Sun can tell us about the properties of the materials they're passing through. So initially it was a matter of looking at the frequencies of the Sun oscillating and trying to compare those frequencies with what models predict and trying to adjust the models so that they predicted the right frequencies. In addition, the gas in the Sun drags the waves with it. If the gas in the Sun and the wave are going in the same direction, then it tends to stretch out the wave in the direction that it's going. And if it's going in the opposite direction, it will compress the wavelengths, so you'll see them more with a shorter wavelength. And so by comparing the mode frequencies of waves going in these opposite directions, you can determine how fast the gas is moving that's carrying the waves with it. And so by using this technique in fairly generalized ways, people are now able to deduce a great deal about how the Sun is moving in its interior. Because it's all gas, it doesn't have to move at the same rate, and so we can determine how the dynamical structure of the Sun is actually configured.
Stars with masses higher than about 10 times the solar mass behave rather differently from the Sun. First of all, they're much brighter, and so even though they're more massive, they evolve faster, only live for maybe 100 million years or less. And secondly, when they have used up all their fuel, and that happens through a number of nuclear reactions in the Sun, we think that the nuclear reactions at the moment convert hydrogen into helium. Then as the Sun grows old, the nuclear reactions can continue in the core of the Sun, so helium can fuse into carbon and oxygen. But that's as far as it goes in a star like the Sun. In these more massive stars, this fusion of element into heavier and heavier elements continue up to production of iron. And then the fusion processes stop, and eventually the core of the star collapses, releasing a huge amount of energy in what we call a supernova explosion. And in that process, all the nuclear elements that have been produced in the core of the star is spread in the interstellar space, and then might be used in the formation of new stars and new planets. And so what we believe has happened is that in the original universe, created in the Big Bang, there was only hydrogen and helium and very small amounts of other elements.
Here in Leuven, let's say, we study massive stars. So these are born with more mass than the Sun, and they live quite a different life than the Sun. And so the most important thing that we discovered, let's say, the past 2 decades, you could say, is how stars rotate in their interior. So the gaseous layers, they rotate around the central core, and we have been able to measure that rotation which is quite different from the surface rotation. You only see the surface of the star, but thanks to the stellar oscillations, we can understand how they rotate in their interior. And so we are mapping that out now, thanks to the space missions that give us sufficient data to unravel that for many stars. But now in the future is the next stage, because once you know how a star rotates in its interior, you also can get a better handle on how the chemicals mix inside the star. And so chemical mixing, as we call it, is really determining how the stars live their life in a much better way than when you don't know anything about this chemical mixing. And so our next step is to use the information and the knowledge on the stellar rotation that we have gained the past few years, and to try to use that to exploit in more detail the properties of the stellar oscillations, and to derive the mixing properties of the chemistry of the star. The more materials mix, the longer the nuclear fusion can keep going inside the star. So this is really the crucial thing if you want to get good stellar ages. And stellar ages, of course, they determine how long the stars live. And when a star dies, it gives away its energy very violently in the stars that we are studying, but it also gives its chemicals that it created during its life back to the galaxy. And that then makes new stars. And so they get richer and richer in metals. Now, if you think of that as human beings, like we are here thanks to a lot of metals that we have here on our planet, and also oxygen and nitrogen, etc. So the chemical evolution of the Milky Way is really made thanks to the stars. And so if we understand better how long they need to do that to make these materials and to give them back, then the chemistry cycle of the Milky Way will become way better determined. And that is really of vital importance if you want to understand how our universe evolves, but also how life on possible exoplanets in our Milky Way would come to be or not.
Oh my goodness, congratulations. It's just amazing work. Congratulations.
Oh, it's wonderful stuff. I mean, starquakes, and I hope I'm not trivializing by saying that, but I just want to know, before we get into the actual substance of this, is what got you interested in this in the first place? I mean, I know that, Roger, you built yourself a planetarium as a child, which even won a prize in San Francisco.
Well, yes, that was part of my initial interest in astronomy, was trying to identify the constellations. And I spent a year watching the constellations come up, and each week or each month there'd be a new set because of the Earth going around the sun. And I had this planetarium, this star atlas, the Norton Star Atlas, which has big sheets of paper that have the positions of the stars on them. And I was using that to identify the constellations. I mean, there's a lot of bright constellations everybody knows. Orion is certainly a magnificent thing to see in the winter sky. But there's other constellations that have fainter stars, and I was using the atlas to identify those. And when I finished that, I thought, these sheets look like they could fit together. And so I traced out the sheets and punctured little places for each of the stars that were on the sheets. And then I taped these, I think it's about 8 sheets on around the center, the sides and the top and the bottom, and I taped them together and put a planetarium light in the center, and was able to project the sky onto a central room that was in our house where there was no light, no windows, but that worked. So it was kind of just a curiosity does it work? And it does.
Yeah. And Jørgen, how about you? What got you interested in astronomy?
Well, I think I was interested in science from a very early age, and astronomy, of course, is a very interesting part of science. And at some point when I was possibly in high school, I really wanted a telescope. And we couldn't afford it, so I decided to build one myself. And just like Andrew, I ground the mirrors for a telescope and put it together and got something that actually worked reasonably well. But then also I was very interested in physics and also beginning to be interested in simple computations. And that really was what brought me to stars as objects, as we said that also in the video, because they are astrophysical objects that you can study in great detail. And so you are able to apply physics to the understanding of the stars to an extent that, at least at that time, you couldn't do for galaxies or for the universe as a whole. And I think that really drew me then in the direction of understanding the stellar internal physics. And then the oscillations came as a complete surprise and a complete bonus, allowing us to do these very detailed observations that we're now using to study the interiors of stars.
That's brilliant. So, you were talking about starquakes before, and we're familiar with the term seismology, but people aren't perhaps familiar with asteroseismology, so and helioseismology as well. So maybe, Jørgen, can we start with you in terms of asteroseismology and then move into helioseismology?
Yes. What we're doing there is to observe how the surface of the star moves in regular patterns and regular waves. And these waves have specific frequencies that depend on the internal properties of the star. And that really is very similar to what the geoseismologists do when they have an earthquake, then they have waves propagating through the Earth with speeds given by the internal conditions in the Earth, and then they measure the arrival of these waves at different parts of the surface of the Earth. And from that, they can then basically invert the data and infer what the internal structure of the Earth is. In our case, we have motions of the stars all the time, but we can still extract the regular frequencies, the eigenfrequencies, just like the tones of an organ pipe or the tones of a bell. And those tones we can then mathematically determine, and we can then compare what we measure with the tones that what we call a model of the star would have, and then see how well the model agrees with the observations. And when I say model, what I mean is that we take all the physics we know from the Earth, and then we take this huge jump to say that physics also applies in everywhere in the universe, including inside the stars. And that allows us to compute numerically what the conditions, predict basically what the conditions are inside the sun and inside other stars. But of course, we all know how good weather predictions are. So we really want to test whether our predictions of the internal properties of the stars are correct. And that's where these measurements of the oscillation frequencies allow us to go back and see, are the models reasonably correct, or how should the models be improved? And in that way, we then learn about how the physics that we use in computing the models has to be changed. And then we learn about properties of matter inside stars.
Mm. And so, Roger, take that on and the helioseismology.
Well, the helioseismology actually started with the discovery of the oscillations on the surface of the sun. Initially, people didn't really know that the sun's surface was oscillating, and the fellow who really made the big breakthrough was Bob Layton at Caltech and using the Mount Wilson Observatory facilities. And he invented a way of imaging the surface Doppler velocities of the material and using a photographic subtraction technique. This was all before we have the digital cameras that we're all so familiar with now. At that time, there was no digital option available. And so he invented this photosubtractive thing and discovered that, in fact, the sun is moving up and down with this.
Bouncing almost.
Yeah, each part of the sun, the sun's a big ball, and you point your instrument at a little piece of the surface, and you see that piece of the surface is going up and down with this 5-minute period. And the thing that I try and tell people about is that he wasn't actually the first to see the sun oscillating that way, that there were several other observatories where it was seen. And in fact, at Mount Wilson, Bob Howard had noticed that a yardstick, which was attached to his spectrograph, was going up and down with 5-minute period. And he thought, oh, that's kind of odd. But he didn't pursue it, and he didn't announce it. So when a year or so later, Bob Layton and his group studied these things and announced it, and everybody said, oh, the sun is oscillating, and this is something that we should learn more about. So that was kind of the beginnings of helioseismology. It was finding that there was some motion there that you could use to analyze the sun.
And Jørgen, in the film, we heard Conny talk about one of the most important questions of the past 2 decades was understanding how stars rotate in their interior. Could you just tell us a bit more about Conny's contribution to the field?
Well, we know, of course, stars rotate. We can see the sun rotating on the surface by following the way the sunspots move across the surface of the sun. And we know that the sun is not rotating as a solid body. The equator is rotating more rapidly than the poles. But what the waves that we observe in the sun when we do helioseismology are advected. They're moved about with the flow inside, the rotational flow inside the sun at a rate that's on an average of the rotation over the part where the wave is propagating. And so by combining the data from very many different waves, we can then probe how the rotation varies as a function of where we are in the sun. And so what we see is very curious behavior, because the outer layers of the sun rotate more or less like the surface. The poles are slow, the equator is fast. And then as you get to a point about a quarter of the solar radius into the sun, then we have a sharp transition, as sharp as we can see it, to rotation that's more or less uniform, the same everywhere. And you could say, then what? I mean, of course, it's interesting to understand why this happens, and in fact, we don't yet understand physically the reason for this behavior. But also this region where the rotation changes very rapidly has a strong effect on the magnetic fields in the sun, and it's probably what drives the variation we see in the magnetic activity of the sun, the fact that sometimes we have very few sunspots, and now we are moving towards very many sunspots and good chances of northern lights in Denmark and Norway. And we have this variation, and the mechanism for that is probably driven by this variation in rotation in the interior parts of the sun. And I would say that's one way where helioseismology could have some practical importance, by perhaps eventually, years from now, making us able to predict how this changes, and then allowing us to prepare for huge solar eruptions that is driven by these phenomena.
Yes, so, we shouldn't forget solar eruptions are one of the huge risks that we face as a human race.
Yes. It is a big risk, actually, for us.
I know in the UK it's second on the risk register after pandemics.
Is it?
Yes, yes. So, Conny mentioned that you can. One of the things that this information has given us is information on the age of stars. What else does it give us? Because this technique is fascinating in and of itself, but it's also given us a lot more information about stars behave.
Yes, the huge step forward in asteroseismology, applying these techniques to other stars, came with the NASA Kepler mission. And in general, I think, and we should maintain that, a very great deal of the honor for the development of this field goes to the people who have designed the fantastic instruments and space missions that we use to get these data. And with Kepler, we've been able to apply the techniques we knew from the sun to a very large range of stars. And I think of course, we want to understand, and that's what I'm doing, trying to understand the properties of stellar interiors. But we can also use that to characterize stars that host planetary systems, what we call exoplanets. And we can determine the age of these stars, and we have found planetary systems that are twice as old as the Sun and the Earth. So that had been around for 5 billion years when the Earth was formed.
Wow.
And then you can sort of try to imagine how these planetary systems have evolved, and possibly how life on these planets in these systems have evolved in these 10 billion years.
Roger, what do you think in terms of exoplanets and finding that sort of Goldilocks zone of planets that are habitable?
Well, the first
so when we're talking about exoplanets and finding, that star that might be like our sun and being able to have a planet that's habitable in the way the Earth is, do you think that's something that's going to happen in our lifetime?
Well, that's a little bit more of a crystal ball than I have, but it certainly is, I think, technically feasible. I mean, the difficulty with planets around stars is the central star is so bright that you have a hard time distinguishing what the planet's like. Some of them are wide enough that you can do it now with the space telescope, the James Webb. But the other technique is that when the planet passes in front of a star and these stellar occultations occur, you can look at the spectral lines that come from the gas passing through the planetary atmosphere and possibly deduce what the atmospheric structure, composition is. And that's a feasible technique, but whether we'll have instruments that do that effectively enough is something that you can't really predict. We'll try, obviously. People are very engaged with that question. It certainly tops on people's lists of things they'd like to know.
Yeah, absolutely.
Now you've got these techniques, what are the questions, the unanswered questions that now seem within reach thanks to the kind of techniques that you've been developing? I mean, what's your number one question that you still want answered?
My question, of course, is a little bit different because I'm mostly engaged in studying the sun, and in particular, all of my last 25 years or so of research has been using the Doppler signals and the magnetic signals visible on the surface of the sun, as opposed to the helioseismology, which looks to the interior. But the surface motions of the sun are very complex, and trying to figure out exactly what's happening is difficult. The polar regions are especially difficult to study because the light from them comes obliquely, and the recent spacecraft that are out there are going to higher orbital latitudes around the sun, and we'll be able to see the polar regions for the first time without having to look a slanty view across the top and sort of figuring out what it is. So that'll be very interesting. I'm trying to get the data from the higher latitudes, but it's complex, and I have some recent results that are from that, but they're just being submitted for publication in a recent research note. But it appears that there are periods when the material on the solar poles is actually flowing backwards. Most of the time the material from the equator is pulled up and then goes up to the pole and goes down. But at sunspot minimum, it goes in reverse for a few years. And that's something that I hope gets a little bit of attention.
Excellent.
Now.
Ladies and gentlemen, you heard it here first. Just want you to know that at Kavli, backward flow on the sun, extraordinary.
Right.
And how about you? What are the big questions for you?
Well, it's really carrying on what I've been doing all my life, trying to understand the physics of stellar interiors. And the big issue there is to understand how rotation evolves. We believe the stars start out rotating very rapidly, and then somehow they slow down to what we see in the sun and in other stars now. And the processes involved in that involve hydrodynamical flows, instabilities, magnetic fields probably, and are extremely complicated and very poorly understood up to this point. And then there are also aspects of other aspects of the physics of stellar interiors where we see issues that we don't understand, and when we then have to go back to our friends, the atomic physicists, to try to understand better the properties of matter under the very extreme conditions that we have inside stars, the way radiation interacts with matter and so on. So these are very active research fields, even after many decades of these studies.
The magnetic fields in the sun are extremely complicated, and you kind of think that we'd be able to understand them, but we keep coming up with new mysteries every time you learn a little bit more. And being able to at least weakly detect the magnetic fields below the surface of the sun is definitely a big advance for us. But so far, the mechanisms for solar variability are still really quite poorly understood. Even though we've studied the sun for several hundred years, it still eludes us how to explain things.
Now, we journalists love astrophysics because you give us fantastic pictures. I mean, just wonderful pictures. And it could be said that actually, of all the sciences, you're the ones who package your research best because you give us these wonderful images. And of course, we're going to get, there's huge huge interest in the James Webb. There's new generation being excited by space with Artemis 1 and Artemis 2. So what do you think that's going to do, all that interest, to the area that you work in?
Well, I very much hope, and I'm agree very well with Andrew there, that I hope it's going to maintain the curiosity of young people and keep them interested in trying to understand the world around us. And in that sense, it doesn't matter so much. Of course, I find astrophysics the most interesting science, but keeping more young people going into the sciences and continue developing our understanding of stars, of the universe as a whole, of plants. This curiosity, I think, is so important, and I think the brilliant astrophysical pictures that we see, and James Webb has been amazing for that, is something that can help maintaining this interest in the natural sciences and strengthen it, and thereby continuing the evolution that we've seen in our understanding of the world around us, which is really the main thing that we're all doing, all of us here as Kavli laureates.
That's really important, yeah.
I think one important factor in having people moving to new parts of the moon and setting up shop, so to speak, in some sheltered crater at the North Pole where they hopefully can find water, and the concept of people out there exploring this new environment, getting out with their hooks and whatever they are using to pick up the material and use it the way people use things in ways that we anticipate and in ways that we don't. The human touch to space exploration, I think, is something that really gathers the imagination rather strongly. And I think that kind of vision of people doing the exploring in these really difficult environments, I think that's going to be a big draw to people and maintain interest. They're, of course, very cautious because if you have a disaster of some sort, it takes on an even more magnified result. So it's a difficult task, but people are trying to do it. And I think the Artemis is a good first, an essential first step to carrying out this work.
Absolutely, yeah.
And if you had your time again and you were starting out now, would you like to be an astronaut? Would you like to be one of those people?
No, not me. That's for somebody else.
How about you, Jørgen?
Well, I don't know staying with the range of today's meeting, I find neuroscience so absolutely fascinating. The fact that we are beginning to understand a very tiny bit about what goes on in the brain might have been something that could have attracted me if I started out now doing science, but astrophysics is fun. I love it.
You can have some questions for this afternoon for the neuroscience laureates as well, yes. Oh, that's brilliant. I mean, I feel like we could talk all day on this. It's amazing. And I love the idea that it's that sort of mysteries, questions lead to yet more questions. Yes, some answers, but yet more questions, which again is that sort of curiosity in the science. Yes. Please do congratulate Jørgen and Roger once again. Congratulations.